Welcome to an example of a change of two variables for a double integral using the Jacobian. In the first video we showed that when converting to a new coordinate system, we often have an extra integrating factor in the new coordinate system, and we can determine that integrating factor using the Jacobian as we see here. So for example, if we convert a double integral over the region R in terms of x and y into the uv coordinate system as defined here, we convert the function into a function in terms of u and v, and then differential a is equal to the Jacobian times du dv or dv du. So this Jacobian gives us the extra integrating factor in the new coordinate system. Let's go and take a look at an example. Here we have a given double integral over the region R, and we're going to redefine the integrating region based upon letting x equal 2 times u and y equaling 4v plus 2u. Let's first sketch the given region of integration. We can see here that x is on the closed interval from 0 to 2. So here's x equals 0, and here's x equal 2. And y is on the closed interval from x to x plus 4. So let's graph y equals x. That's a line with the slope of 1 passing through the origin. That would be this line here. And notice that y is above this line. And let's go ahead and graph y equals x plus 4, and y is below that line. So we have a y-intercept of 4 and another slope of 1. So the given region of integration is this region here. And now we're going to redefine the integrating region based upon x equals 2u and y equals 4v plus 2u. So let's go ahead and list the vertices of this region in terms of x and y. So we have the origin, 0, 0. Then we have 0, 4. Then we have 2, 2. And then we have 2, 6. Now I want to determine what the vertices would be in the uv coordinate system. So let's go ahead and solve this equation for u. We would have u equals x divided by 2. Let's go ahead and solve this for v. So we'd first subtract 2u and then divide by 4. If we sub in x over 2 for u, we would have y minus x divided by 4. So we'll use these two equations to find the vertices in the new coordinate system. To determine u, we'll just divide x by 2. So this would be 0, this would still be 0, this would be 1, and this would be 1. And then for the new v coordinate, we'll have y minus x divided by 4. So 0 minus 0 divided by 4 is still 0. 4 minus 0 is 4 divided by 4, that's 1. Here we're going to have 2 minus 2, that's 0 divided by 4, we have 0. And we have 6 minus 2, that's 4, divided by 4, that's 1. So notice how the new region of integration is much simpler. We have 0, 0, 0, 1, 1, 1, and 1, 0. So our new region of integration is just a 1 by 1 square, which is going to simplify our limits of integration. So before we set up the new double integral, let's go ahead and find the Jacobian or integrating factor when converting to the uv coordinate system. So here's our Jacobian. Let's start by determining our partial derivatives. So the partial derivative of x with respect to u, that's just going to be 2. The partial derivative of x with respect to v, that's going to be 0. And now we'll have the partial of y with respect to u. That's going to give us 2. And then partial derivative of y with respect to v, that's going to give us 4. So our Jacobian is going to be equal to this 2 by 2 determinant. So we'll have 2, 0, 2, 4. So we'll have 8 minus 0, which is equal to 8. So when converting to the new coordinate system, we'll have an extra factor of 8 in our double integral. So let's go ahead and set this up. We're going to rewrite the given double integral in the uv coordinate system. So the given function was x times y, which will be 2u times 4v plus 2u. And then the Jacobian was equal to 8, so we have an extra factor of 8. Now let's go back and take a look at our region of integration again. Both intervals for u and v are from 0 to 1. Let's integrate first with respect to v from 0 to 1, and then with respect to u from 0 to 1. And we could have easily switched this order of integration. Let's go ahead and evaluate this on the next page. If we distribute here, we would have 8uv plus 4u squared times 8. So we can see there's a common factor of 4 here as well as this 8. So I'm going to go ahead and factor out 32. That's going to leave us with 2uv plus u squared dv du. Integrating this back to v, we'll have 2u times v squared over 2. The 2's will simplify out, so we'll have uv squared plus u squared v. Remember, we're substituting in for v, so when v is 1, we'll have u plus u squared, and then when v is 0, these will both be 0. So we'll have 1/2 u squared plus 1/3 u to the third. So we're going to have 32 times, when u is 1, we'll have 1/2 plus 1/3. And then when u is 0, these will both be 0. So 32 times, this will be 5/6. And this simplifies to 80/3. So just remember, when converting to a new coordinate system, we do have to make sure that we calculate the Jacobian to determine the extra integrating factor. I hope you found this example helpful. Thank you for watching.